So very good evening to the students who have joined. So kindly can you let me know in the chat box if my voice is audible and my video is visible. And also if the presentation is visible to you. Okay, thank you so much. So we will wait until more students join, then we will start today's session. Okay. Okay, so I think we can start. So, very good evening to the students who have joined. My name is Moshumi Dev and I am a PMRF fellow from the Department of Chemistry and Chemical Biology, IIT ISM Dhanbad. So, today it is the week 7 live interaction session for the NPTEL course of Medicinal Chemistry. Today we will solve about 20 questions regarding your week 8 course contents. Okay, so we will discuss 20 MCQs which are related to your week 8 course content, and it will be from mostly some question will be from previous years and some question will be new. So I think it will be better for you to learn new things. Okay, so I think we can start with the session. So as more students will join, I will just add them up. And so can you just write in the chat box if my voice is audible and everything is fine, like my video is visible and you can see the slides also. So if you have any doubt, any problem during the session, you can write in the chat box, okay, always, and I will solve in between. And when I am telling you a question and we are discussing something, I want you all to participate in it. Okay, so it is better if you try to answer those questions, and it is okay if the answer is wrong or anything, but it is important for you to try to answer those. Okay, so I think we can start slowly, and eventually when others will join, I will just add them up. Okay, so it is the week 7 live interaction session. So the first question of today's session is, which of the following statements best describes structure activity relationships, SAR. So structure activity relationships, it is abbreviated as SAR, and in most of the places you will have questions which only will tell you about use the term SAR, not the structure activity relationship, because it is a very well known term in medicinal chemistry and very important too. Now, so your first question, it is related to the SAR. So it says that, which of the following statements best describes the structure activity relationships? Option A, the study of which functional groups are important to the chemical reactivity of the drug. Option B, the study of the physicochemical properties that are important to the absorption of the drug into the blood supply. Option C, the study of the structural features of the drug that are important to its biological activity. And option D, the study of the structural features of a drug that are important to its chemical stability. So you have to identify among these four which is the correct statement regarding the structure activity relationship. Okay, so we have one answer. So again, for the students who have joined late, I will just repeat once it again. Okay, so which of the following statements best describe structure activity relationship? Option A, the study of which functional groups are important to the chemical reactivity of the drug. Okay, somebody wants to join again. Okay, so we have two answers for this question. So the students who have joined late, I will repeat the first question. So today it is the week 7 live interaction session, and here we will discuss about the week 8 course contents. Okay, so the first question of today's session was, which of the following statements best describe structure activity relationships, or SAR. Now as I said before, like SAR is a very popular term in the medicinal chemistry, and it is very much used and very much important when you are designing a drug or a chemical compound which is intended to have a biological activity. Okay, so which of the following statements best describe structure activity relationships? Option A, the study of which functional groups are important to the chemical reactivity of the drug. Option B, the study of the physicochemical properties that are important to the absorption of a drug into the blood supply. Option C, the study of the structural features of the drug that are important to its biological activity. And option D, the study of the structural features of the drug that are important to its chemical stability. So try to answer this question. Okay, already we have two answers, and the two answers are saying it is the number C. Others also try to answer it. So, as I say every day, like I want every student who are present in the class to try to answer the questions which are shown. Okay. So, it does not matter if your answer is correct or wrong, but it is very important for you to at least try to answer this question. Otherwise, you won't know that how much of the course you have understood so far. Okay. So, it does not matter if your answer is correct, it is wrong, because I will show you I will show you anyway what is the correct answer, but for you to try is the very important. Otherwise, the class won't be, if it is not interactive, we don't serve the purpose of having this kind of interaction session. Okay. So, already we have 2 answers. So, I will wait for 2 more minutes if others also want to answer this question, and then I will just show you the answer and we will discuss about the structure activity relationships in detail. So, do we have some different answer or any others? Okay, very good. So, everybody thinks it is number C. Now, let us find out which is the correct answer. So, yeah, very good. It is the correct answer is number C. So, what is the SAR? SAR is the study of the structural features of a drug that are important to its biological activity. Now, we will discuss about the SAR in detail. So, structure activity relationships, in short, the structure determines the function. So, it is presented by Brown and Fraser in 1865. The structure of the compound determines its biological effect it has. Determination of the structure and function relationships helps medical chemists synthesize new drugs and pharmaceutical agents. So, as you can see from this figure, so say it is a drug. Okay. So, it has a 3 ring A, ring B and ring C, and we have a trimethoxy type of functional substitution here. Okay. And here we have a NHCOMe kind of group which is in dashed, and here is the ketone group and OMe group also here. So, each and every group, each and every ring has a particular biological effect. As you can see, this methoxy group, O-methoxy group, it has a important for biological binding ability. This methoxy, it is not required much, this fourth one. So, we can remove this methoxy. Okay. This methoxy, it is important for correct conformation and activity. This methoxy, this permits halides and alkyl alkoxy amino SME, but not bulky group. This ring, it allows it allows ring contraction. Okay. This NHCOMe can be replaced by other substituents, but the epimer diminishes the activity, means it has a dashed bond here. So, you can change this substituent, but this dashed bond must be in dashed form, okay, not in the bold form. So, as you know, it is the chiral center and it has below the plane, above the plane structure. So, the bond, it should be below the plane, not the above the plane. Okay. So, here we have a unsaturation which increases the activity, and ring expansion is not permitted here. So, this was some features for the structure relationships which determines the biological activity of the same compound. So, as you know, in the drug discovery process, when you are designing a compound to be a drug, you design few similar compounds all together. Okay. So, a series of compound has to be generated, and then you just vary some substituent to see how much biological activity it differs. That is how we come up to a lead compound in a drug discovery program. So, again I have a example for SAR. So, see, so this compound, it is a RET inhibitor in the lung cancer. So, RET is a kinase. Okay. So, kinases are some enzymes which actually transfers the phosphate group from ATP to the protein substance. Okay. And this reaction, it actually catalyzes many reaction or many functions in our body. Many signal pathways are stimulated by these kinases, and some cancer compounds, cancer cells also, they are stimulated by the cancer. So, inhibiting these kinases actually inhibits the cancer, and it is a very new cancer therapy which is introduced in 2001 actually. So, this compound, it is an example of a RET inhibitor which is used in the lung cancer. So, as you can see, this is this part, this is the main pharmacophore, and these are which are in the pink, in the red and in the blue. So, these are the places where we can change or we can vary to see how the function or activity it varies. Okay. So, as you can see, this blue one, Okay, so it is for so 5 tertiary butyl isoxazole and 3 tertiary butyl N-methyl 1H pyrazole are more favorable in this position. So this is the actually isoxazole, and you can change it with the pyrazole. Pyrazole means say here you have N 5 member ring N and O, right. So pyrazole have actually 5 member ring where we have N, here N we have, and we have NH. Okay. So in the place of this oxygen actually we will have a NH. So it is the pyrazole. So we can change this part with this part also. Okay. So we have to keep this functionality same. Okay. So for having same results you can actually change this one with this one also. So these two groups are most favorable in this position. Now 1,3 substitution pattern completely attenuates the activity. So here as you can see, if you have 1 or 3 substitutions, so as you can see this benzene ring, it has 1 and 4 substitution, right. So here these two group bonds are para to each other. But if you had this bond from this position, not in this position, if two bonds we have, if these two bonds had the 1,3 substitution pattern, but this compound will not be active then. Okay. And for this part as you can see, polar groups are more preferred here. N-methyl pyrazole and methyl sulfonine phenyl groups are showed best results. So this is as I said, N-methyl pyrazole means this kinds of, here we will have a methyl group. So this group and this group are most favored here, and this is the pharmacophore of the compound, and sulfur in the place of this NH nitrogen, it diminishes the activity several fold, and methylation also diminishes the activity. Means if you change this NH with the sulfur, or if you change this NH with NMe, means this hydrogen, if you substitute this hydrogen with a methyl, then the activity of the compound will be diminished very much. Okay. So that is how the structure activity relationship works. That is how when you design a compound, you have to change the substituent, you have to design a series of compound by changing some structures, and then you will come up with a compound which can be used as a drug. So this is all about the structure activity relationship. Okay. So I think you have followed whatever I have told you till now, and if you have any doubt regarding this structure activity relationship or this problem, you can tell me in the chat box. Okay. So did you understand that part? This part, this SAR is very important. I think A is also correct. Okay. So A, what was the A? The study of which functional groups are important for the chemical reactivity. No, actually it is said, as you say, that it is the chemical reactivity, right. So for the SAR or structure activity relationship, we do not see at the chemical reactivity, we see the biological activity. Okay, here the medicinal chemistry differs from the synthetic organic chemistry. Okay, so not chemical reactivity for which we are concerned. We have only concern how the biological activity differs. Okay, chemical reactivity means you can say that you can replace one functional group with a or more reactive or less reactive functional group. But what will the effect that functional group will have in the biological activity? What biological activity will be shown by this chemical reactive or chemically unreactive compound? It is our major concern, not the chemical reactivity. Okay, so in that case A is not the correct answer for the SAR. I think it is did you understand what is SAR, and I think what I discussed so far, the examples. So did you understand that much, or I have to repeat anything? See, when I am saying you a question or anything, yeah, okay, good. So if you have any doubt at any point, it is better at that time you tell me in the chat box. Okay, after every question I will check the chat box and I will answer this query. Okay. So this was all about of SAR and problem number 1. So now we will move toward our next problem. Okay, so it says that N-phenylethyl morphine was synthesized from the morpholin and found to have enhanced activity. Okay, so actually it will be actually morphine, not morpholin. Okay, what design drug structure was used here? So basically in this question, this is the structure of the morphine, and N-phenylethyl morphine was synthesized from this morphine. Now from here to here you have to identify what drug design strategy is used. Number A, simplification. Number B, extension. number C, rigidification, and number D, conformational blocker. Now you have to identify from morphine to N-phenylethymorphine which structure drug design strategy has been used here. Is it simplification, extension, rigidification, or conformational blocker? See the structures carefully and read the all options carefully, and try to answer it in the chat box which of the following you think is the correct answer for problem number 2. So anybody has answered it yet? Okay, extension, number B, number C. So okay, we have few answers for it. So let us check what is the correct answer. So B and C and extension. So we have 2 extensions and 1 rigidification. So let us see what is the correct answer. So the correct answer for this question is number B, extension. Okay, so before going to the answer, I will just correct it here. It will not be morpholin, it will be morphine. Okay. So as you can see, what is the difference between these two, morphine and which is the difference between this N-phenylethymorpholin. So I will highlight it. So here you see in the morphine we have this N and we have this methyl group here, okay, and for this compound we have this chain here, we have this from this methyl we have this CH2 and then phenyl ring, okay. So what are the so it is the extension of the basically one bond, it is extended in this compound here, okay, and we have extension. So it is the extension which is the drug design strategy. So the drug design and for optimizing binding interaction, the various drug design method are used, okay, and the aim of the drug design by optimizing binding interaction is to optimize the binding interaction with the target. The reasons: to increase the activity, reduce the dose level, to increase the selectivity and reduce the side effects. And the strategies which are used for the drug design are vari-alkyl substituent, vari-aryl substituent, extension which is used here, chain extensions or contractions which is more or less similar to this extension only, and ring expansions and contractions, ring variation, isostars, simplification, rigidification. Okay, so these are the strategies which are used for the drug design, and the motto or aim of the drug design is to optimize the binding activity so that the activity and selectivity are increased but dose levels and side effects are decreased. Okay, and structure based drug design, this is the example of the extension strategy. So as you can see, there is a drug molecule, okay. Now you can just extend it by using a chain and increasing a chain here and adding a chain up here, so that it can fit in the target. So if it is the target cavity and if you had only this drug, the previous one, it won't be a good fit in the drug cavity, okay. But if you have a extension here and extension here, so as you can see, it will be fitting in the drug pocket more in a better way, okay. So that's how we just use the drug design strategy and for the optimization, okay. So this was for an example of the optimization, okay. So it was the problem number 2. Now I will just check if there is any doubt regarding it. Okay, I think it is clear to all. I will then move toward the next problem today. So problem number 3, it says that SAR shows that the important binding groups in the morpholins are phenol, aromatic ring and amine. A diagram can be drawn which shows these functional groups and their relative orientations. What is the term for it? Number A, pharmacodynamics. Number B, pharmacokinetics. Number C, chromophore. Number D, pharmacophore. So read the question carefully. Here we have asked about a term which is used in this case, like SAR shows that the important binding groups in the morpholine are phenol, aromatic ring and amine. The diagram can be drawn which shows these functional groups and their relative orientations. What is the term for this? Number A, pharmacodynamics. Number B, pharmacokinetics. Number C, chromophore. Number D, pharmacophore. In previous classes, we discussed more about pharmacokinetics and pharmacodynamics. The other two terms are new to you today, but use your previous classes knowledge to answer what is pharmacokinetics, what is pharmacodynamics and what should be the correct term for this question. So, again I want everybody to try to at least answer this question. It does not matter if your answer is correct or wrong, but at least try. Okay, so we have till now 2 answers which says number D. Okay, so 3 answers for D. Okay, then let us check out. Okay, so the correct answer is pharmacophore. Very good, number D. Now we will look at each and every term again. So as we all know, what is pharmacodynamics? Pharmacodynamics is the study of mechanism of action of drugs and explains what the drug does to the body and how do they do it. It tries to explain the action effect relation as well as dose relation effect. It involves the drug receptor interaction to elicit the action of the drug in the body. Pharmacodynamics is the study of the biochemical and physiochemical effect of the drugs and the mechanism of action, and it provides the basis of the rational use of drugs and the design of the better and effective drugs. And what is the pharmacokinetics? Pharmacokinetics is the quantitative study of the drug movement in, through and out the body. It is the study a process by which the drug is absorbed, distributed, metabolized and eliminated from the body. The absorption, distribution, metabolism, excretion all involve its passes across the cell membranes. Pharmacokinetic properties are affected by the route of administration and the dose of the administrated drug. So, basically as I said a bit before, I think, so easy way to remember pharmacokinetics and pharmacodynamics is, the pharmacokinetics is what our body is doing to a drug. So, you are taking a drug. So, what our body is doing to that drug? It is absorbing the drug, it is distributing the drug in the all part of the bloods and the all tissues, it is metabolizing the drug and it is eliminating the other unessential part of the drugs from our body. And what is the pharmacodynamics? It is what the drug is doing to our body. I mean how the drug is acting on our body, on our system in by exerting its biological activity. Okay. Now, what is the chromophore? So, it is a Greek word, chroma means color and force means barrier. The defined as any isolated covalently bonded group that shows a characteristic absorption of electromagnetic radiation in the UV or visible region. Compound containing chromophore is chromogen. Okay. So, if a compound have a ability to absorb the radiation in the UV or visible region, it is the chromophore, the part which absorbs the color, which is called the chromophore, like C double bond C, C double bond O nitro, these are called the chromophore. And pharmacophore. So, IUPAC definition of a pharmacophore is an ensemble of steric and electronic features that are necessary to ensure the optimal supramolecular interaction with a specific biological and to trigger or block its biological response. Okay. So, hydrogen bond donor, hydrogen bond acceptor are. So, in drug design, the term pharmacophore refers to a set of features that is common in a series of active molecules. Hydrogen bond donor, hydrogen bond acceptor, positively negatively charged group and hydrophobic regions are the typical features. We will refer such features as pharmacophoric group. So, in short, if I have to give you an example for pharmacophore, I will show you the previous one question which we discussed today. Yeah. So, this one, in this question we discussed about a drug. Okay. So, as you can see this drug, as you can see this part we changed here and we changed in this group, but we keep this part constant. Okay. This part which is basically pyrrolopyrimidine. Okay, this is this group, it is called, okay, it is also we can call 1 2 3 4 amino pyrrolopyrimidine. So as you can see, when we will we have keep it black because we will not change this part. So in a series of drug, when we do the drug discovery I mean part drug discovery series, we keep one part of the drug same. Okay, so in a series, one part or one group or one ring, it will be same, and other based on that we will change the other substituent. So the part which is kept constant, it is very important for the biological activity of the drug, which cannot be changed at any cost, and that part is called the pharmacophore. Okay, so this was an example of the pharmacophore. We will see more examples later. Okay, so this was all about the pharmacophore, pharmacokinetics, pharmacodynamics and everything. So I think it is clear to all what is a pharmacophore, and let me check once. Okay. So this was the problem number 3. Now I will go to the problem number 4. Okay. So which strategy of the drug design was used to develop protonethol thelol from the adrenaline? So as you can see, this is a drug adrenaline. This is adrenaline, which is a hormone, actually not a drug, and this is the pronetholol. Okay, so this pronetholol was designed from this adrenaline. So what is the drug design strategy is used here? Ring fusion, number B simplification, number C rigidification, and number D chain extension. So identify which of the following is the correct answer. Is it ring fusion, simplification, rigidification, chain extension? When you are designing pronetholol from adrenaline, which of the following drug design strategy is used? Okay, do we have any answer? Number A. So everybody thinks it is number A. Okay, let us check it. Okay, very good. So the correct answer is number A, or ring fusion. So ring variation or ring fusion. So it is very easy. If you can see here, we have two free OH groups, and we have just fused a ring here, okay, in the blue part. So it is the ring fusion. So this let us take a look about this drug, which is pronetholol. So it is a beta blocker. Now what is this is from this in the design from adrenaline, okay, and it is selective for the beta receptors over the alpha receptor. Now what is a beta, what is alpha, and what is this agent? So basically beta blockers or beta adrenergic blocking agents or beta antagonist or beta adrenergic antagonist. So these terms are similar, okay, for the beta blockers. This is a class of drug that are particularly used for the management of the cardiac arrhythmias, protecting heart from the second heart attack, myocardial infarction after the first heart attack, secondary prevention, and hypertension. So basically beta blockers are a class of the hypertensive drugs. Hypertensive drugs means it is used to reduce your pressure. Okay, so sometimes the beta blockers are used to reduce your blood pressure, and sometimes in the blood pressure there are different kind of hypertensive drugs. Okay, there are ACE inhibitors, which we had I think discussed last in last class. Okay, the angiotensin converting enzyme inhibitor, which is used to lower the blood pressure by lowering the volume of the blood, and the so there are many drugs for as which are used as a hypertensive, and this beta blockers are one of them. So it is basically used when the in the blood pressure when the palpitation happens, means your heartbeat it is beating very fast at some times, okay, and you have some type of panic attack. So this drug is also used at that time. And in the most of the patients who have who have less age, okay, who are younger, the younger patients who have hypertensive, they are actually given this beta blockers for also anxiety and keeping the heartbeat normal. Okay, so this is one very important example for the beta blocker. So now we will move to our next problem. So problem number 5, it says that which of the following major aims in drug design is not related to the pharmacodynamics of the drug. Number A, reduction of the side effects. Number B, the maximization of activity. Number C, reduction of the toxicity. Number D, maximization of the oral bioavailability. So you have to identify which of the following major aims in the drug design is not related to the pharmacodynamics. So these 4 are the major aims for drug design. Your drug, you must take care of the reduction of side effect, maximization of activity, reduction of toxicity and maximization of oral bioavailability. But one of these 4 terms is not related to the pharmacodynamics of the drug, which pharmacodynamics we just discussed, I think, in the question number 3. Okay. So you have to identify which of the following major aim of drug design is not related to the pharmacodynamics. Again, I want everybody who are present in the class to try to answer this question. So anybody has tried answering it? So rigidity of the compound, right? Introducing an aromatic ring leads to the rigidity of the compound, right? Yeah, definitely. So if you actually add a aromatic ring, so if you have a, I think, free functional group, okay, so if you have 2 sides free, so it can rotate at any side. But if you are fusing a part of a bond with the aromatic ring, so it will lead to the rigidity of the compound, okay, because in that way the true bonds which were free, they are not free to move anymore, okay. So it is correct. Now for this question we have 2 answers, B and D. Okay, let us check out what is the correct answer for the it is B or it is D for the question number 5, I think. So yeah, if you can see rigidification, yeah, I got it what your point is, but here as you see, let me just show you one example. So here as you can see, we already have a ring, right? Here in adrenaline we already have a ring and we are just adding up a ring which is fused with others. So basically we are having a naphthalene kind of ring right here. So here we have a naphthalene kind of ring. Okay, sorry. Okay, sorry. Okay, here as you can see, here we have this naphthalene type of ring. So this is called a fused aromatic ring. So from a normal aromatic ring you are having a fused aromatic ring. That's why this strategy, it is called the ring fusion. Okay. Now what you are saying, it is correct, like introducing an aromatic ring, it will rigidify the compound. Okay, it is completely fine. But as you can see, like we will have some example of rigidification soon, but for your understanding, I will say, so say if you have this kind of ring, okay, here, so here you say you have some functional group here, some functional group here, and you have this kind of blocking here, okay, chain here. So as you can see, this is a normal free chain of carbon carbon, so it can rotate in any way, so it is very flexible. But if you have this kind of thing and then you have this kind of a benzene ring in between and then you have this kind of ring, So you are changing this part with this kind of benzene ring. Okay, so that's how you are rigidifying this part. Now this part is not free to move like it was here. So this is called the rigidification. Okay, and here since we are having one phenyl ring already in the compound, and you are just joining another phenyl ring, making it as a fused aromatic compound. That's why it is called the ring fusion. Okay. So I think it is. Did you understood how what is the reason behind calling it ring fusion, not rigidification? Got it. Okay, very good. So we will have the example for the rigidifications in the other question. Today we will have it, I think. So let us move toward the next what we are discussing here. So yeah. Okay, so the correct answer is the maximization of oral bioavailability is not a major aim. It is not related to the pharmacodynamics. So as we discussed, like what is the objective and aims. So pharmacodynamics can be defined as the study of the pharmacological effects of the drug, so and their mechanism of action. The objective of the analysis of the drug action are to understand the interactions between the drug and the target cells and to characterize the fuel sequence and the scope of action of each drug. So, as I said, the aim of the pharmacodynamics is to study how the drug is acting on our body. So, as I said, it should not have many side effects, it should have maximum activity, but it should not have high toxicity. Okay, so these three are related to the pharmacodynamics, but the maximization of oral bioavailability is not generally related to the pharmacodynamics, because the bioavailability is not something which is related to the pharmacodynamics. It is how the drug is available in our body is not matter how the drug is acting on our body, right. So this is not example or related to the pharmacodynamics. So as you can see, this flow chart, which is very important flow chart. So the drug is administered, drug is absorbed, it is distributed, metabolized, eliminated. This whole part is taken care of by the pharmacokinetics. So the bioavailability, it is also, we can say it is somehow related to the pharmacokinetics, but not the pharmacodynamics. What are the things which are related to the pharmacodynamics? It is the regulatory protein, where the receptor enzyme, ion channel transporters, binding to the molecular target, affinity, action of the drug, response and efficacy. These are related to the pharmacodynamics. Okay. So this was all about your pharmacodynamics. Now we will move toward the next problem. Okay. So which of the following intermolecular binding interaction are possible for the secondary amide? So secondary amide and primary amide. So you just think about the structure of the primary secondary amide, and the options are hydrogen bonding only, option B van der Waals attraction interactions only, option C ionic bonds only, option D both ionic bonding and hydrogen bonding. So for secondary amide, which of the following binding interactions are possible? Just think about the structure of a secondary amide, and that is how I think you will be able to answer this question easily. So which of the intermolecular bonding interactions below are possible for a secondary amide? Hydrogen bonding only, van der Waals interaction only, ionic bonding only, both ionic bonding and hydrogen bonding. Hydrogen bonding only. Okay, we have number 2 number D and 1 hydrogen bonding only for the answer. So as I say, just think about the structure for the D, and we have hydrogen bonding. Just think about carefully about the structure of a secondary amide. Okay, I will just show you the answer, then we will discuss it. Okay, so the correct answer is hydrogen bonding only. So let us just go to the secondary amides. Okay, so So as you can see from here carefully, so this is, we can say it is a secondary amide. Now the very good example for the secondary amides is, so just let me ask you a question. So in the biological system, where you see this kind of secondary amide bonds, which is very important to us, where in the biological system we see secondary amide bonds. Any idea? Where in the biological system we see the secondary amide bonds? It is very popular and very well known thing, and if I say, you will just know it. So where we see this kind of bonding, this kind of CONH bonding in the biological system? Any answer for it? Okay, let me tell you then. So in peptides, in the here in the peptide, where we have the peptide linkage in the proteins, so where there we have this kind of secondary amide bonds, right. So as you know, in the peptide what we have a carboxylic acid, and we have a amine, and we have the CONH, then R, then CH2, then we have a CONH, okay, that kind of thing. So in the secondary amines, what we basically have the hydrogen bonds only, okay. So this NH of the secondary amine, it take part to the hydrogen bonding with the NH, and that's how the alpha helix and beta sheets, those things are formed, like the secondary structure of the peptides, right. So how it is the hydrogen bonds only. So there are different kind of bonding interactions. Let us check out a few of them, like ion dipole interaction. Okay, so ion dipole interaction, what is the ion dipole interaction? So if you have one ion, okay, like let us say we have one ion like Na plus ion, okay, and we have a dipole, okay. So dipole, it is not a ion, it has a dipole moment, okay, like OH bond, hydroxyl OH bond, it is a dipole, it has a dipole. So what is a dipole? Dipole is like this kind of bond, where you have a delta minus and delta positive charge. So this bond is a covalent bond, but we have a gradient of charge, which is called the dipole, like this kind of, okay, positive negative interaction. So if you have a sodium plus ions, let us say, and you have this OH kind of bond, and the interaction we will have, it is called the ion dipole interaction, okay. And then we have a hydrogen bonding interaction, which is explained here, okay, the delta positive, delta negative, and if you have a delta negative, delta positive here, okay, we have this hydroxyl, and you have another hydroxyl here, which is here delta negative and delta positive. The interaction here, it is the hydrogen bonding interaction. Dipole dipole interaction, so we have this the kind of a dipole and dipole interaction, okay, and like this you can see here are the examples for everything. Ion and induced dipole. So ion induced dipole is something like in a compound, if you do not have a dipole moment, let us say, but if you have I mean one compound is inducing dipole of the compound. So say you have dioxygen, okay, here, and it is not in dipole moment here, because oxygen it has own the same electronegativity. But if you have a ion, say if you have Fe2 plus ion here, and in presence of this Fe2 plus ion, this oxygen will be delta negative, this oxygen will be delta positive. There will be a shifting of the charge, okay, from here to here. So that's how this is called the ion induced dipole, means this compound does not have a dipole moment itself, but in presence of a ion, it is inducing some dipole moment. Dipole induced dipole, similar like ion induced dipole. And dispersion of London force, it is basically the van der Waals interaction, all you can say. So this is all about it, okay. So I think it is clear. So do you have any doubt till now? Yeah, in peptide bonding, right. Okay. Okay. So this was the problem number 6. Now let us check out next problem. Okay, problem number 7. It says that cocaine was isolated as the active principle from the coca leaves. Studies into SARs show that it is important functional groups for bonding are those shown in blue. What binding interactions are likely for the aromatic ring will happen? Okay. So number A, hydrogen bonding as hydrogen bond donor, hydrogen bonding. Number B, hydrogen bonding as hydrogen acceptor. Number C, van der Waals interaction. Number D, ionic bonding. So as you can see, this is the structure of the cocaine, and the blue part which is shown in this figure are important for the biological activity. Okay. So what are the binding interaction are likely to be shown for the aromatic ring? So for this aromatic ring, what is the binding interaction will be shown by this compound? Okay. Is it hydrogen bonding as hydrogen donor, hydrogen bonding as hydrogen acceptor, van der Waals interactions, or ionic bonding? Again, try to answer this question till the correct answer. So do we have any answer for it? Number A, and van der Waals interaction. Okay, we have one number A and one van der Waals interaction. Okay, let us check out the answer. So others, you also try to answer. We have only 2 answers till now, but I want others also to participate. It does not matter if your answer is correct or wrong, as every day I say, like, it does not matter if the answer is correct or wrong here, because but it is important for you to try to answer it. Okay, we have van der Waals interaction, number B, number A. So we have a variety of answers here, I think. So let us check out. Okay, so the correct answer is number C, van der Waals interaction. Okay, so why? Okay, so here we are what is the question which is asked here? So it is asked that the important functional groups are shown in blue. What binding interaction are likely for the aromatic ring? So in the question it has been asked for only this part which binding interaction will happen. Okay, so when a compound will be acting as a hydrogen bond donor or acceptor, when there will be a hydrogen bond. Okay, so there is a hydrogen which is present, or there is a dipole present. Okay, so as you see, which hydrogens are capable. So here you can say that there are hydrogens present in the phenyl ring, right? But are those hydrogen capable of forming a hydrogen bond? The answer is no. So which hydrogens are likely to participate in a hydrogen bond? So if you have a compound like A, let us say it is a A and there is a H. So what are the property of this A which will lead to the hydrogen bonding? So the one and most important, like it should have higher electronegativity than the hydrogen. Okay, like oxygen, OH, NH. These bonds are capable of forming the hydrogen bond as a hydrogen donor. Okay, since the electronegativity difference is very high between the oxygen and nitrogen and hydrogen, so here there will be a dipole change, delta minus, delta plus. Here also we will have a dipole change, delta minus and delta plus. So these hydrogens are capable of giving the hydrogen bond, and the ketone groups, okay, and this kinds of group, the groups which have lone pair or electronegativity or negative charge like O minus, okay, these are capable of acting as a hydrogen bonding acceptor. But the phenyl rings, mostly they participate for the van der Waals interactions, or very popularly known as the pi-pi interaction. Means there is a, if there is a phenyl ring here and it is a planar, right, it is a plane, and there is a phenyl ring in just below the phenyl ring, other phenyl ring. So you have a pi-pi interaction, means the pi electrons of the one phenyl ring will interacting with the pi electron for the other phenyl ring. Okay, so which is popularly known as the pi-pi interaction. So if we have this kind of phenyl ring here, okay, so it has some pi orbitals, as we all know, right. So these are the pi orbitals which form these double bonds in the phenyl ring. And in the lower plane, if you have same as this kind, so this pi orbital can interact with this pi orbital of the lower ring, which is called the pi interaction. So or pi stacking. So the energy for this interaction is 0 to 10 kilocalorie per mole, which is a very weak electrostatic interaction between aromatic rings. There are two general type, phase to phase or edge to edge. So, phase to phase can be happening or edge to edge happening. Phase to phase pi stacking interactions are responsible for the slippery feel of the graphite. Similarly, pi stacking interaction helps stabilize DNA double helix. Okay. So, this is about the pi stacking and van der Waals interaction. So, I think it is clear. Okay. So, if you have any doubt regarding any question at the end of the question, please feel free to write that. I will just describe it once more. Okay. So, do we have any doubt in this question, why it is the pi interaction, why not others? Okay. So, if not, I will move toward the next problem then. Okay. So, problem number 8, it says that the following hypothetical structure has an asymmetric center marked by the asterisk. Okay. And which of the following structures might be worth synthesizing as an analog of above lead compound in order to achieve an active compound lacking an asymmetric center? Your options are A, B and C, and the options I mean the structures are A, B and C, and options are structure A, structure B, structure C and all of them. So, this is a hypothetical molecule here, okay, and from the asterisk it has an asymmetric center, okay, and which of the following structures might be worth synthesizing as an analog of the lead compound in order to achieve an active compound lacking asymmetric center? Means we have to synthesize a compound which will not have a asymmetric center here, which is presented here. So, it is it structure A, structure B, structure C or all of them? So, do we have any answer for it? All of them, structure B, number C. Okay, so we have few again different answers for it, which is good to have some different answers. Okay, let us check the answer. So, it is number D, all of them. So, all of them can be the lead compound, can be the analog which lacks the asymmetric center. Now, before going to detail in the problem, let us check out what is the asymmetric center. So, this is example of a asymmetric center. So, chiral molecules, generally molecules that contains an asymmetric center. Asymmetric chiral center means a tetrahedral atom bonded to 4 different groups, indicated as the asterisk. Okay. So, a tetrahedral atom bonded to 4 different groups is said the chiral asymmetric center. Okay. What is the rule for a compound being a chiral asymmetric center? Only sp3 hybridized atoms can be a chiral. Okay. Note, molecules may appear to be different until you go out several atoms. Okay. So, only sp3. So, as you can see carefully, this carbon, it is a sp3 carbon, and we have 4 different group bonded to it. One is this methyl group, okay, one is this hydrogen group, one is this part of the chain, and one is this part of the chain. So, this is basically a carbon which is bonded to 4 different group A, B, C and D from this. So, this is a tetrahedral carbon. So, if you see the structure of A, B and C carefully, so here this is the first carbon which is after the ring, okay, this carbon is the first carbon after the ring. So, which is this one. So, here you can see this carbon, it is not a sp3 hybridized, right, this carbon is sp2 hybridized because it has a double bond here. Okay. So, this it cannot be a it lacks asymmetric center. Okay. So, structure A, it lacks a asymmetric center which can be an analog for the lead compound because other part is the same, only it has a double bond. Okay. For number B, it is also a compound which lacks a asymmetric center because this is a nitrogen and it is not a sp3 hybridized. Okay. and this is also a asymmetric center, number C, because it has a this kind of cyclopropane ring. So, this part and this part is same. So, it is basically a it does not have 4 different groups. Okay, it has 3 different groups, we can say. So, all of them can be an analog for the lead compound in order to achieve the lacking asymmetric Cox center, because all of this 3 does not have any asymmetric center. So, but all of 3 actually they are the analog for this hypothetical lead compound. Okay. So, is it clear why the answer is all of them? If you have any doubt at any point, please feel free to ask. Okay. C has an asymmetric center? No, C does not have an asymmetric center. So, if you look at the structure carefully, let me just maximize it. So, as you can see the structure carefully, this part, this is a different group, right? This is also a different group, but what about these 2 bonds? These 2 bonds are basically same, because you can see it is a CH2 here, okay, here is also CH2, and if you go from this part to this part, both are the same bonding. So, this compound is basically C, A, B, D and D type of molecule. This D this part is same, and this is A and B, these parts are different. Okay. So, it is not a asymmetric compound, or this is not a chiral compound. Somebody wanted to join, I think. Okay, so did you understand? C does not have an asymmetric center. That center is same. Just think about how if this carbon was bonded to a methyl group here, Me here, Me here. You are just bonding those 2 similarly, but that bond is same, right? If you go from here to here or here to here, it is same. It is not some different molecule. So, it does not have 4 different group. So, it does not have a asymmetric center. Okay, in structure B, the nitrogen has the sp3 hybridization, but just read the thing carefully. Okay, what about the asymmetric centers? As I mentioned, asymmetric centers, it must have 4 different group. 4 different group should be there, but if there is a nitrogen, okay, it is the nitrogen, it has 3 different group, one methyl, one this phenyl ring and one this ring. Okay, so it does not have 4 different moieties. So, that's why it is not asymmetric. And basically asymmetric and the chiral centers, it is actually mostly in the organic, it is mentioned for the carbons. Okay. So, carbon centers are basically the asymmetric centers, not other molecules. Okay, like nitrogen, oxygen, they does not counted as the asymmetric center. Okay. So, the only carbon which is can be have a sp3 hybridization for 4 with 4 different functional groups. That is why carbon centers are mainly said as the asymmetric centers. Okay. Now, we will move toward the next problem. Okay. Problem number 9, it says that combristatin is an anti-cancer agent discovered from an African plant. Analog 1 is more active than combristatin, whereas analog 2 has less activity. Which strategy is used here for designing analog 1 and 2? Okay. The options are number A, simplification, number B, isosteric replacement, number C, rigidification and number D, chain contraction. So, this is combristatin, this is analog 1, this is analog 2. Okay. And now analog 1, it has more activity than combristatin, and analog 2, it has less activity than combristatin. Okay. So, which structured design strategy has been used here? Is it simplification, rigidification, isosteric replacement or chain contraction? Okay, look at the structures very carefully and then try to answer this question. Meanwhile, when you are at this question, so this is already 1 hour of today's class. Okay, so just take a few minutes, 2 minutes for looking at the question. Okay, I am just giving you a 2 minutes break. In the break, look at the structures carefully and write in the chat box. I want everybody to answer this question. Which of the following you think is the correct? So, I am not leaving, I will just off my camera and my audio, but the presentation will be on, I will be on the call and I will just join after 2 minutes and I will check the answers and then we will discuss the further questions. Okay. So try to answer the question. So hello, I am back. So we have few answers. We have isosteric replacement, number B and number D. Okay, so is my voice audible and my video is visible to you? Can you confirm? Yeah. Okay, very good. So okay, let us discuss it. So we have few answers for it. Now let us check what is the correct answer. So now here we have come to the part rigidification. So it is the rigidification. Okay, somebody wants to join. So in previous one question we had the part somebody has asked the aromatic rings are rigid and or not. So here the thing we used is the rigidification. Isosteric replacement is something different. Okay, I will just come up to isostars and isosteric replacements later in today's class. Okay, that is a different thing. So the correct answer is the rigidification. Now what is the rigidification? So as you can see, it is the example of the combristatin, which is an anti-cancer drug. So this bond, okay, this bond, it is a free bond. Okay, so this bond can be rotated, this part. Okay, this bond can rotate as it want, but when you are making it a double bond, means if you are making it like sp2 hybridized double bond, okay, so what you are doing, you are just rigidifying the bond. Okay, now the bond, it cannot rotate 360 degree, right? This, when it is a single bond, it can rotate 360 degree, but if you are, it is a double bond, it is being rigid. Okay, now it cannot rotate freely in the free space. Okay, this is the strategy, example of the rigidification strategy. Okay, and this analog, it is a Z isomer, and this analog is a E isomer, and the Z isomer can be in it form only, and the E isomer can be only in form, and this analog is more active, this analog is less active. Okay. So, this is the example for the rigidification. In the previous one question, I was one of you just asked about the rigidification. So, this is the example for the rigidification, because we are rigidifying one free rotable bond, which the bond which is free to rotate, we are just rigidifying the bond and we are just stopping the rotation of the bond. Okay. So, now I will quickly move toward the next problem. Problem number 10, it says that succinylproline was the lead compound for captopril, which act as an inhibitor of angiotensin converting enzyme. What is the relevance of the thiol group? So, as you can see in the captopril, here we have a thiol group which is not present in the succinylproline. So, what is the relevance of this thiol group? Number A, it can form a covalent disulfide bond with the cysteine thiol group in the active site. Number B, it acts as an isostar for the carboxylic acid. Number C, it acts as an bioisostar for the carboxylic acid. Number D, it is a smaller group than the carboxylic acid and fits into the binding site more easily. So, from this succinylproline to captopril, we have the change of this part, and we have introduced a methyl and thiol group here in replacing this carboxylic acid group. So, what is the relevance of this thiol group in the captopril? So, is it the options are number A, it can form a covalent disulfide bond with the cysteine thiol groups in the active site. Number B, it acts as an isostar of the carboxylic acid. Number C, it acts as a bioisostar for the carboxylic acid. Number D, it is a smaller group than the carboxylic acid and fits the binding site more easily. So, identify what is the correct answer, what is the relevance for the thiol group. We have answers number D, B, C and A. Okay, we have 4 answers for it. So, very good. We have some multiple answers, which is good. Okay, let us check out. So, the correct answer is number C. It acts as an bioisostar for the carboxylic acid. Now, what is bioisostars? So, bioisostars, I will just take a laser pointer. Okay. So, bioisostars are the substituents or the groups with similar physical or chemical properties which produce broadly similar biological properties in a chemical compound. In drug design, the purpose of exchanging one bioisostar for another is to enhance the desired biological or physical properties of a compound without making significant change in the chemical structure. Okay. So, as you can see, this is a aminopyridine which is a drug, and this is the propylphenazone. Okay. So, aminopyridine, it is marketed as the analgesic and anti-inflammatory drug in 1896. In 1922, it was revealed that aminopyridine was a carcinogen. Okay. So, propylphenazone developed by Roche in 1951, bioisostatic modification of the dimethyl amino group removed its carcinological action. So, this drug was introduced at first in 1896, but it was revealed that it was carcinogenic. So, this person Roche, what he did, he just replaced this dimethyl amino group with only this propyl type of group. okay, and it removed the carcinogenic action. So, this but this chemically these two groups are comparable, okay, but these two groups have a very diverse biological action. That is why this is called the bioisostar of this group. So, because bioisostar are the substituents that are similar in physical and chemical properties, but produce broadly similar biological effect in the in drug design. The purpose of exchanging one bioisostar for another to enhance the desired physical and chemical biological properties. Okay. And this propylphenazone and propylphenazone, paracetamol, caffeine, these three are actually used for a trade name of the Saridon. Okay. This was the example of the bioisostar. Now, I will move toward the next problem, the problem number 11. So, it is also related to the bioisostar question. So, it says that which element acts as a bioisostar of the hydrogen. Options are number A deuterium, option B fluorine, option C both, option D none. So, for the bioisostar of hydrogen, is it deuterium, is it fluorine, is it both of them, or is it none of them? Try to identify the correct answer. Which element acts as a bioisostar of hydrogen? So, for the previous one, do we have any doubts? Deuterium, we have C, and I think, I do not know, option, I think number D and number C. Okay. Others also try for the bioisostar of the hydrogen. Is it deuterium, is it fluorine, is it both, or is it none? So, do we have any other answers for it? Both, number D, B, C, D. Okay, let us check what is the correct answer. So, the correct answer is number C, both. So, both deuterium and fluorine can act as a bioisostar of the hydrogen. So, deuterium as an isostar of hydrogen, strategic development of deuterium at the sites of metabolism where hydrogen atom abstraction can disturb metabolism and redirect the metabolic pathway. So, this is an example where the deuterium is used as a bioisostar of the hydrogen, like this compound which is called the paroxetine, which is a GSK inhibitor kind of thing. So, this compound is inactive, this compound inactive CYP2D6. Okay, so, this compound has a toxic effect because of the inactivity of CYP2D6, but when you change this to hydrogen here, so if you can see carefully, there are two hydrogen atoms here, right? There is one hydrogen here and one hydrogen here. If you replace two hydrogen with two deuterium, so okay, so this compound, the deuterated compound, relieves the inactivation of CYP2D6. Okay, so this is called the CTP347. Okay, so that's how hydrogen can be replaced by deuterium, and these are examples for a selective serotonin reuptake inhibitor, SSRI inhibitors, SRIs, okay, which are a class of antidepressant. And for the fluorine, the unique properties of fluorine have led to its widespread application in drug design as an isostar of hydrogen. Since incorporation of fluorine can productively modulate a range of properties of interest to medicinal chemists. Okay, so, the hydrogen, the van der Waals radius of hydrogen is 1.20, the van der Waals radius of fluorine is 1.35. Okay, 20% of all drugs are fluorinated compounds. So, because of so, if you will be surprised to know that fluorine has a very good biological effect. Okay, that is how why 20% of all drugs which are exist in the world, it have this fluorine atom. So, these are few examples of fluorinated drugs. So, improving metabolic stability, one of the strategies to counter lower metabolic stability is to block metabolically labile site with a fluorine substituent and hope that the small fluorine atom will not impair the binding the target protein. Okay. So, this is an example for the cholesterol absorption inhibitor, which are the hyperlipidemia, which are used for hyperlipidemia. Okay. So, this compound it is a lead compound. Okay. And if you can see, it has a I mean dosage of 2.2 milligram per kg, but because it has a very low metabolic stability, means you have to take much of too much of drug to get to have a substantial amount for the biological activity. But if you just replace hydrogen here, here we have a hydrogen and also we have a OMe here. Okay. So, if you replace these groups for with the fluorine, so this compound it has a the ED50 of 0.04 mg, which is much lower. So, this was the examples where the deuterium and fluorine both can be used as a bioisostars of the hydrogen. Okay. So, this was your problem number 11. Now, I will quickly move toward the next problem. So, do we have any doubt or any question for it? Okay. So, many of you have answered correctly, like it is both. Again I am saying it does not matter if your answer is correct or wrong, but try to answer the questions. Okay. So, problem number 12, it says that which of the following is the most frequent protein ligand interaction? Number A, hydrogen bonding interaction. Number B, pi-pi interaction. Number C, ionic interaction. Number D, hydrophobic interaction. Now, from these 4 interactions, you have to identify which of the following is the most frequent protein ligand interaction. Is it hydrogen bonding, is it pi-pi interaction, is it ionic interaction or hydrophobic interaction? All of you try to answer this question in the chat box. Hydrogen bonding. So, I think all of you think it is hydrogen bonding. Okay. But we will see what is the correct answer. Okay. So, correct answer is number D, hydrophobic interaction. So, hydrophobic interaction is the most frequent interaction in the protein ligand interaction. Okay. Hydrogen bonding, I think it is the most frequent or interaction in the amino acid or protein interactions, but for the protein ligand interaction, hydrophobic one is the most frequent protein interaction. So, this is the frequency distribution for the most common non-covalent interaction observed in the protein ligand extracted from the PDB. So, PDB is a protein data bank basically here. Now, so in PDB we have all existing protein which for which the structures can be determined till now. Okay. In the world, it is deposited in that protein data bank. So, if you if we have the if you check the every structure for the protein ligand interaction, you will find this is the protein ligand interaction frequency distribution curve. So, the most frequent is the hydrophobic interaction, which has the number of interaction almost I think 65,000 times. Okay. So, the hydrophobic interactions are the most frequent. After that, we have the hydrogen bonding, which is around 30,000. Okay. So, hydrogen bonding is the second most frequent in the protein ligand interaction. The first one is the the hydrophobic interaction, and then the third one is the pi stacking interaction, the pi-pi stacking, which I have shown you earlier. Then we have weak hydrogen bonding interaction, like for the CH and O, which is also called the aromatic hydrogen bond interaction. Then we have salt bridge interaction, amide stacking interaction and cation pi interaction. So, if you look at carefully, so I do not know, I think you have not seen it yet, but eventually if I get a chance I will just show you in the last class when we finish everything. So, we have, if we have a protein core or protein, so it is basically a there is a cavity in the protein, okay, and if the ligand fits into the cavity, the most frequent interaction is the hydrophobic interaction, which is normal. With the hydrophobic interaction means normal van der Waals interaction, the carbon carbon interactions, also the interactions between the electronic cloud of a ligand and the electronic cloud of the protein. So, which is the most important? We have hydrogen bonding, but it is very fewer. Okay, the hydrogen bonding interaction, it is most important interaction in the secondary protein structure, like in the alpha helix, in the beta sheets, but in the protein ligand interaction, the most important or most frequently happening interaction is the hydrophobic interaction. Okay. Okay, so this was the problem number 12. Now we will move toward the next problem. So, problem number 13, it says that the use of one drug for activating different targets is called number A, additive therapy, number B, combinational therapy, number C, MT or multiple target therapy, number D, none of the above. So, if you are using only one drug, okay, for example, here you can see in this diagram. So, we are using only one drug, but it is stimulating two targets, and this has a synergic or additive therapeutic effect. So, what is this therapy called? Is it additive therapy? Is it combinational therapy? Is it MT therapy or multiple target therapy, or none of the above is correct? Take some time and try to answer this question. So, do we have any answer for it? MT therapy, number C. Okay, so the most answers are number C or MT therapy. Okay, let us see. Okay, very good. So, the correct answer is MT therapy or multiple target therapy. So, what is the advantages of the MT therapy or multiple target therapy? Let us check it out very quickly. So, when we are using one drug to stimulate two different targets and both have a activating, it is called a multiple target therapy. Okay. So, what are the advantages? The higher efficacy against complex diseases such as cancer. So, in the cancers, you know it is very difficult to use different drugs for doing it, but one drug, if it can target different hit different targets, so it will have a very better activity, which is called the higher efficacy. Okay. More predictable and superior pharmacokinetic and safety profiles as a consequence of administering a single drug. The combination of multiple active principles may result in positive but also negative synergistic effect, which limits the number of useful combinations. The probability of developing target based resistance simultaneously to multi-target drugs is statistically lower than the probability of developing resistance against the single target drugs. The risk of drug-drug interaction associated with combination therapies is avoided and the therapeutic regimen is greatly simplified. The use of drug cocktails often complicates dosing schedules and negatively impacts patient compliance. It is even more difficult to perform clinical trials with drug combinations if the drug came different companies. Okay, so these are the advantages of this multiple target therapy or MT therapy. So now I will quickly move toward the next problem. So problem number 14, it says that what is the reason of improved activity of the B than A? Number A, less toxic metabolite formation. Number B, increased solubility. Number C, increased bioavailability. Number D, good pharmacophoric profile. So as you can see, this is the structure A, this is structure B, all of the thing is the same, only there is a nitrogen in place of carbon from A to B. That's why the B has the improved activity than A. Now you have to identify which is the correct reason behind this. Number A, less toxic metabolite formation. Number B, increased solubility. Number C, increased bioavailability. Number D, good pharmacophoric profile. So do we have any answer for it? So in cancer there are different targets. How? Okay, so in cancer what happened, like if you know, like there are malignant cells, right? So in the sometimes the cancer is localized. Okay, so in the one place in the body that you have the cancer, but the cancer cells are affect the body in different parts. Okay, that means it lowered the immunity and in different targets. So if you treat the cancer in different in a way, like you are taking different drugs to I think to hit the different targets or hit the different problems you are having due to one part in due to malignancy in one part of the body. So it will be difficult because the body cannot take different drugs in that case. Okay, because your immunity is lower, your pharmacokinetic pharmacodynamics profiles will be very low. Okay, one drug will cause toxicity for the other part. And so in that part, that's why how we use the MT therapy. And about this MT therapy and cancers, we will discuss in detail. I will discuss these things in the last class of this sessions. Okay, so because we are one class earlier, right? So today it is week 7, but we are discussing week 8 course materials. But when we will have the week 12, so we will have completed every week. So with that day I will discuss some additional things, that when I will just discuss this thing more detail. Okay, because it cannot be discussed today because it is a very big topic, but we will discuss it later. So I think number D is for the last question which I repeated, right? Okay, let's check the answer. So the correct answer is for this question number 14 is number A, less toxic metabolite formation. How? Now the question is how. Now you can say it is has the less toxic metabolite formation. Okay. So always remember, when you have this kind of profile, like whenever you have this kind of paramethoxy, or we have this kind of phenol quinol type of thing, these things are toxic for the body, this paramethoxy or paraphenol, because these form this quinone type of which is a toxicophore. Okay, you know the term pharmacophore. Now one term is toxicophore, means the structure features which are toxic for our body, like this quinone ring. This quinone ring, wherever this quinone ring will form, it will be toxic for our body. Okay, so which is called the toxicophore. Now if the compound is this much, so when it is metabolized in vivo, so it will be forming this toxicophore quinone. Okay, but if you are replacing this carbon with this nitrogen, okay, and it is this compound, when it is metabolized in vivo, so what will happen, it will form a non toxic amide. Okay, it will not form a quinone, there will be a NH here, and it is a amide which is non toxic to the body, and this compound is a HIV1 attachment inhibitor, anti HIV compound, and this compound is known as the BMS 488043, which is in the phase 3 clinical trial. Okay, and from going from there here to here, it also increases the aqueous solubility and the less toxicity, but the less toxicity is the main reason for the improved activity of this B rather than the A. So, always remember this quinone is a toxicophore. Wherever there is a chance of having this paramethoxy or para-OH, we will have this kind of quinone formation which is toxic. Okay. So, I think it is clear now. I will move toward the next problem. So, problem number 15, it says that by which method chimeric drugs are formed. Number A, in silico drug designing method. Number B, pharmacophoric hybridization method. Number C, bioisosteric replacement. Number B, structure based drug design. So, chimeric drugs are formed by which method? In silico drug designing, pharmacophoric hybridization, bioisosteric replacement, or structure based drug design. So, identify the correct one. We have any answers for it? Number C, number D, number C. Okay. So, bioisosteric and structure based drug designs are the most common answer. Okay, let us check what is the correct answer for it. Okay, so the correct answer is pharmacophoric hybridization. Now, let us check what is the chimeric drugs and what is the pharmacophoric hybridization. So, chimeric drugs, another method of design a chimeric drug that contains key pharmacophoric features from the two different targets. For example, structure containing features of true methoxystriadol and colchicine has been synthesized as a potential anti-cancer agent. Although both of the parent structure have anti-cancer activity, they have serious drawbacks. Okay, so if I give you example, so as you can see, this is the 2-methoxystradiol. Okay, so 2-methoxystradiol is metabolized rapidly, while this 2-methoxystradiol, it is an anti-cancer agent, but it is metabolized rapidly. Okay, and colchicine, which has a toxic side effects. This is colchicine. This is also I think I have shown you this figure just in the first question today. So, this is also anti-cancer drug, but it has a toxic side effects. Okay, and the chimeric structure also has an anti-cancer activity, but improved pharmacophoric properties. So, which is the this is the chimeric drug. Okay, so for the this chimeric drug, what we have this trimethoxy part from this colchicine here. Okay, and we have this 2-methoxystriol, we have this 4 rings and this kind of figures from this 2-methoxystradiol. Okay, and this is the method by which this chimeric drugs is formed is called the pharmacophoric hybridization. Means we are taking to the pharmacophore or the part of the drugs, like we have two anti-cancer drugs, and in the two anti-cancer drug there are some structural features which are important for the biological activity. We are just taking up that two pharmacophore, the two structural parts, and fusing those parts and making a common drug which can be used for the better activity and lesser side effect because of the improved pharmacokinetic properties. Okay. So, this is the method for the chimeric drug formation, which is called the pharmacophoric hybridization. And this is a very important, I think topic of research today, the pharmacophoric hybridization, which is very important and also interesting, and we can just read it once from the internet also, and I will discuss these things more detail in the last class, because when we will finish everything up, we will just go into the detail. Okay. Now, for problem number 16, we have this. It says that number 2 is found to be more interactive with the target rather than the parent lead one. Why? So, this is the parent lead compound and this is the number 2. So, number 2, it is more interactive with the target rather than number 1. Why? A. The strategy used was one of the ring expansion. Number B. Blue nitrogen allows better solubility. Number C. Blue nitrogen can act as a hydrogen bond donor. Number D. The strategy used could be described as extension since further binding interaction has occurred. So, you have to identify the reason why 2 is more interactive with target rather than parent lead 1. Number A. Strategy used was one of the ring expansion. Number B. Blue nitrogen allows better solubility. Number C. Blue nitrogen can act as hydrogen bond donor. Number D. The strategy used could be described as extension since further binding interaction has occurred. So, do we have answers for problem number 16? Option C, option B. Okay, option B, option C seems to be most frequent answers. Option B or option C. I think option D or option C, I think. So, let us check. So, the correct answer is option D. The strategy used could be described as extension since further binding interaction has occurred. Okay. So, one advantage of alternating an aromatic ring to a heteroaromatic ring is that it introduces the possibility of an extra hydrogen bonding interaction with a binding site and should be suitable for binding region available, which is an extension strategy. For example, structure 1 was the lead compound for a project looking for a novel antiviral agent. Replacing aromatic ring with pyridine ring has resulted an additional binding interaction with the target enzyme. So, as you can see, this is a phenyl ring, right. If you replace this phenyl ring with this pyridine ring, so what will happen? We are introducing one nitrogen atom. This nitrogen atom has a lone pair, right. So, this lone pair can act as a hydrogen bond acceptor and it can just interact with the it can interact with the target enzyme, which is not possible in a way which is not possible for this compound, because we do not have a nitrogen or a lone pair here. So, the strategy used here, it is described as an extension strategy since a further binding interaction has occurred, which was not present in the lead compound, but is present in the B, and that is the reason why number 2 is the more interactive than the number 1 lead compound. Okay. So, did you understand it? Number C, number B. Okay, I think we had only one answer for it, number D. Others think it was B or C. So, B will not be the answer, okay, because number B as you can see, it is we can it is better solubility. We cannot say it has a better solubility. We don't know it exactly, but and it cannot, number C cannot be the answer, because it cannot act as a hydrogen bond donor, because we don't have a hydrogen here. For hydrogen bond donor, we need an hydrogen like hydroxyl or NH2 amine, and this can be act as a hydrogen bond acceptor. That's how more binding interaction will occur, and this is called the extension strategy. So, now next question is problem number 7. It says that Du-122-290 is more potent and selective than saltopride, because. So, this is the structure of the saltopride and this is the Du-122-290. Okay. So, this is more potent than this one. Okay. This one is more potent than this one, and you have to identify the reason. Number A, pyrrole ring has made it more rigid. Number B, replacing amide moiety has improved lipophilicity. Number C, both A and B are correct. Number D, it cannot be said for sure only from the structures. Now, this is a kind of diplomatic question. Read the options carefully, look at the structures carefully, and think what can be the correct answer for this question. So, Du-122-290 is more potent and selective than saltopride. What is the reason? Options are: number A, pyrrole ring has made it more rigid. Number B, replacing amide moiety has improved lipophilicity. Number C, both A and B are correct. Number D, it cannot be said for sure only from the structures. Okay, number C, I think everybody thinks. So, we have 3C, 1B and 1A. Okay, let us check what is the correct answer. So, the correct answer is number A, pyrrole ring has made it more rigid. Okay. So, pyrrole ring of Du-122-290 serves to increase the rigidity of the side chain present in the saltopride. Okay. The red colored bond, it is not mentioned here. I think this is the red colored bond. Okay, it will be okay. Once again, I will show you here. Yeah, so this is the red colored bond, this one. Okay, this in saltopride is freely rotable, but is locked within the pyrrole ring of Du-122-290. This reduces the number of possible conformation that Du-122-290 can adopt and increases the chances of the active conformation being present when it enters binding site, thus increasing activity. Moreover, some of the conformations are now disallowed, may be those which are adopted when saltopride binds to the D2 receptor, thus increasing selectivity for the D3 receptor. Okay, so this saltopride, it is actually intended to be selective toward the D3 receptor. Okay, but due to the freely rotable NH bond, okay, I will show you the highlight the bond. So, this bond, it is freely rotable in this saltopride. Okay, but if you just fuse this and make it a pyrrole ring, this will disallow few conformation of this saltopride, and this conformation may be more binding toward the D2 receptor, thus it will increase the selectivity to the D3 receptor. Okay. So, this is also an example of the rigidification which we have used here for the drug design, like we used in the combristatin. So, this is also an example of the rigidification. So, is it clear to you, or do we have any doubt in this question? If you have any doubt, you can just feel free to write it in the chat box. Otherwise, I will move toward the next problem. So, the next problem number 18, it says that procedure of transforming racemic drugs to single enantiomer is called number A chiral pool, number B asymmetric synthesis, number C chiral switch, number D asymmetric switch. So, we have when you are designing a drugs, if it has chiral centers, always it forms in a racemic form, but the procedure of transforming that racemic drugs to single enantiomer is very necessary. Like we have seen before in before classes, like the example of thalidomide, right, where the R isomer or S isomer, one isomer was actually working as a drug, but the another isomer was working as a toxic or teratogenic, and which was leading to the birth deformity of the fetus, and that is why the having single enantiomeric drugs are very important. Now, the procedure of transforming racemic drugs to single enantiomer, it is called number A chiral pool, number B asymmetric synthesis, number C chiral switch, number D asymmetric switch. You have to identify the correct one. So, do we have any correct answer for it? Number B, we have 3 number B and 1, I think everybody thinks it is number B. Read the question carefully. It says that procedure of transforming racemic drugs to single enantiomer, what is called? Okay, let us check out the answer, then we will discuss it. So, the correct answer for it is the chiral switch. Okay. So, the most common answer which I found for this was the asymmetric synthesis. So, asymmetric synthesis is synthesizing only the single enantiomer. Okay. So, read the question carefully. It says that procedure of transforming single racemic drugs to single enantiomer. Okay. So, you are synthesizing a racemic drug, you have a racemic drug, and then you are transforming, or you are just making the racemic drug we are just separating the enantiomers. Okay. You are making it a single enantiomer. So, this procedure is called the chiral switch. Okay. And the asymmetric synthesis is when you are synthesizing only one enantiomer, not the racemic drugs. Okay. When you are synthesizing only the single enantiomer, it is called the asymmetric synthesis. Okay, means you do not have the racemate, but from separating single enantiomer from the racemic drug, it is called the chiral switch. So, here we have the advantages of the chiral drug. So, chiral drug is a single agent instead of a mixture of two distinct drugs, simplifies the interpretation of the basic pharmacology, greater selectivity for their biological targets, improved therapeutic indices, and the reduced adverse effect, longer or shorter duration of action, more appropriate dosing frequency. Chiral switch is a procedure used to transform an old racemic drug into its single active enantiomer. This new enantiomeric drug developed by the pharmaceutical manufacturer will receive additional patent protection and a new generic name. Okay. So, when you are transforming an old racemic drug to its single new enantiomer, the procedure is called the chiral switch. And asymmetric synthesis is when you are synthesizing a single enantiomer. You are not synthesizing a racemic mixture, you are synthesizing chiral switch. Very good. Okay. So, this was all of it, and again now I will move toward the next problem. So, problem number 19, it says that why number A is more potent inhibitor than number B. So, look at the structures of the number A and number B carefully. Okay. I will just show you. Okay, the options are hydrophobic interaction is more, option B hydrogen bonding interaction is more, option C van der Waals interaction is more, option D all of the 3 options are correct. So, what is the difference between A and B if you look at it carefully? So, see at this part, okay, this part and this part, there are few differences in this part. Okay. So, what is the difference here from this part to this part? this is more potent. As you can see, the Ki or inhibition constant is 1 nanomolar, while the Ki of this is 39 micromolar, means it is very high, the Ki. So, Ki is the inhibition constant for which is used for the inhibitors basically. Okay, so this is very less active. Number A is very less active than okay, so 1 second. Okay, so Ki is the inhibition constant, and I think the A is more potent inhibitor. I think the question is little wrong. Okay, so B will be the more potent inhibitor than A. Okay, so this is wrong. This will be okay. I will just correct the answer later. So the B actually is the more potent inhibitor than A. Okay, the question is just opposite. Okay, B is more potent inhibitor than A, and you have to find out the answer reason. I will just correct it here. So, B, it will be more potent inhibitor than A. What is the reason? Means B is more active than A. What is the reason? What is the interaction which is I mean participating in it? Is it hydrophobic, hydrogen bonding, van der Waals, or all of three? Look at the structure carefully when it differs, and think which of the following interaction can take part here. Do you have any correct answer or any answer for it? Number A, number C, number D. D, C and A. Okay, let us check out. So, yeah, number A, hydrophobic interaction is more. So, this is basically a structure where there is a, I think it is little difficult, but I will just tell you more about this kind of structures in last class. So, the ribbon structure, as you can see in the gray, it is the protein, and the colorful one is the ligand. Okay. So, when you are just having this, we are having this propane, this kind of thing. Okay. So, what will happen? It will introduce the extra hydrophobic interaction part, and because of that it is more potent inhibitor than the A, because here we have only hydrogen, but here we have a carbon-carbon chain which participates in the hydrophobic interaction with the target protein. Due to increased interaction, it is more potent inhibitor, and I will just correct it here. Okay, 1 second, I will just discard and I will just correct this. It will be B and this will be A. Okay. So, yeah, A is the correct answer. Now, the last question, it says that tetrazole is a bioisoster of number A, phenyl group, number B, carboxylic acid group, number C, ketone group, number D, amide group. So, bioisostars, we did discuss a lot about bioisostar today, starting from hydrogens, then fluorine, deuterium, which is the bioisostar of hydrogen. Then we discussed about few about the carboxylic acids also. So, tetrazole is a bioisostar of which group? Phenyl group, carboxylic acid group, ketone group, amide group. Tell me in chat box which of the following you think is the bioisostar of the tetrazole. Or tetrazole is the bioisostar of which of the following? So, let me check if we have any answer for it. There will be no hydrogen bond interaction between isopropyl group and oxygen present near S. Okay. I will come to this part in the last. So, for it, no hydrogen bond interaction between isopropyl group. Yeah, the isopropyl group and the oxygen near S, which is the oxygen near the Oxygen present near S. So what is mean by the oxygen present in near S? Mean, if you are you telling about this oxygen or this oxygen? I don't understand the question. Is it a question or is it a, I mean, S double bond O? Okay, here also is S double bond O, and is it terminal one or the internal one? So anyways, no hydrogen bonding will be possible since we don't have a hydrogen here, right? The propyl isopropyl group, it does not have any electronegative or that dipole hydrogen like OH or NH2. So there won't be any hydrogen bonding interaction. Only interaction possible here was the hydrophobic interaction, and that is also with the target protein, not the ligand will itself take part in any kind of interaction in between. Okay. Okay, I think for the question I had few answers. I think D or A. Okay, let's check out the last question and last answer. So we had the question like tetrazole is a bioisoster of. The correct answer is number B, carboxylic acid group. Okay, so carboxylic acid group in the in our body. So free carboxylic acid group cannot be tolerated. Okay, isoster of carboxylic acid have been studied extensively. These studies have typically focused on enhanced potency, reducing polarity, increasing lipophilicity, means improved membrane permeability, enhancing pharmacokinetic properties, reducing the potential for toxicity. So common bioisosters for the carboxylic acids are like this. These two are most frequently used, and heterocyclic base bioisoster for carboxylic acids are these. Okay, so tetrazole is one of the group which is very common and very fastly used as a bioisoster of the carboxylic acid. So this is an example. Okay, angiotensin 2 receptor antagonists provide instructive insight into the carboxylic acid bioisosteric design, since binding affinity to receptor in a series of biphenyl acids is quite sensitive to identity of the acidic element. Okay, so if it has this compound which is the angiotensin 2 receptor antagonist, which is used for the hypertension. So if there is a R, if it is a carboxylic acid, then IC50 will be 275 nanomolar. Okay. Now if you change this carboxylic acid with different bioisoster of carboxylic acid, so see, if you change this for this group, which is the NHSOCF3 kind of group, the IC50 lowers, which is 100 nanomolar, which is more which has more affinity than the or activity from this carboxylic. Then we have this kind of group which has 25 nanomolar IC50, but the tetrazole, it has the 3 nanomolar, which is very much lower than the original carboxylic acid. So lower the IC50 value, higher is the activity, means using tetrazole has improved the activity of the drug. Okay. So this was the example for the bioisosteric replacement when tetrazole is a very important bioisoster of the carboxylic acid. So this is it for today. So today we discussed many of the question. Please repeat question number 10. Okay, sure, I will quickly repeat the question number 10. Okay, question number 10, it says that succinyl proline is a lead compound for the captopril, which act as an inhibitor of the angiotensin converting enzyme. So this captopril is a angiotensin converting inhibitor of ACE. Okay, and this is the lead compound. From this lead to this compound was designed. But so what is the relevance of trial group? So as you can see, this compound has higher activity than this. Okay, it was actually designed by SAR from this, and this has higher activity. So what was asked, like what is the role of this thiol group? Why this thiol group has higher activity? Okay, so the options were like this. The options were number A, it can form a covalent disulfide bond with cysteine thiol group present in the active site. It acts as an isoster of the carboxylic acid. It acts as a bioisoster of carboxylic acid. Now there is a difference between isoster and bioisoster. Isoster is basically related to the chemical activity, but bioisoster is related to the biological activity. And number D, smaller group than carboxylic acid, and it fits to the binding site more easily. Okay, and the correct answer was number C, it acts as a bioisoster of carboxylic acid. Okay, here we discussed about the bioisostars, what are bioisostars, okay, and this group, this thiol group, and it can also act, this methyl thiol group actually, it also act as a bioisostar of the carboxylic acid. So, as I said, free carboxylic acid are not very good for the drug likeliness in the body. Okay, that is why it is very important to change that free carboxylic group with is a bioisostar. Tetrazole is a very important, very famous bioisostar of carboxylic acid, and that methyl thiol is another. Okay. So, that was it. It was a group week 7 live interaction session. Okay, where we discussed about SARs, we discussed about, yeah, for some books. Yeah, I can actually suggest few medicinal chemistry books, but I do not exactly remember the names right now. So, there is a, I think, a book called Patrick Lamb and somebody, I think, I do not remember it exactly. So, in the next class I will suggest you some name for the medicinal chemistry. Okay, so there is a very good book for medicinal chemistry, I do not remember. Okay, let me check, I have the book, I think. I had the book, I do not remember the name, but I have to check it out. So, there is a medicinal chemistry book, I think. Thomas. So, this is a medicinal chemistry book by Gareth Thomas. Okay, and another book, I think, Silverson and Holiday, and another book is a very good book, which is this. Yeah, so I prefer this book for medicinal chemistry. Okay, so this is medicinal chemistry by Graham L. Patrick. Okay, so this book I always prefer for medicinal chemistry, because it has very good basics and also very good application part. So, you can follow this book for medicinal chemistry, the book for the introduction of medicinal chemistry by Graham L. Patrick. Another book is medicinal chemistry by an organic chemistry, drug design and of the drug action by Silverman and Holiday. You can also read this book, and also you can try this book Gareth Thomas, but I personally prefer this one, this Graham L. Patrick. Okay. So, these were some books. So, did you just write up the names of the book, or I have to show it again? I can show the names again. Okay. Okay, the soft copy, I think you will find it in the internet. Okay, so because if you cannot find the soft copy in the internet, I will just share my email ID here. So, if you cannot, you just search the names. Okay, I will just share my email ID to it. So, this is my email ID. Okay. So, if you cannot find the soft copy of the books, you can just drop a mail to me. I will share you by email. Okay. So, that is how we can work out this thing. So, this lecture PPT and today's classes lecture PPT and the video, it will be uploaded by the NPTEL website. We will share it to them and they will upload it. So, in case you have, if you have missed anything during the class, you just can check it out from there, and just try to download the books from the internet. If you do not have it from the internet, you can just drop a mail to me in this email ID, and I will then share you the soft copy of the books. Okay. So, that was all for today. Next Saturday we will meet with the book with the week 8 live interaction session. Okay. And for now, so goodbye, and let us meet in the next week. Okay. So, if you have any doubt, you also can drop a mail. So, I will just close the session for today. Goodbye. Thank you. So, thank you all for joining. I will just close the session now.